Start with the basics. What exactly is an algorithm? In simple terms, an algorithm is a step-by-step set of instructions designed to solve a specific problem or perform a task. Think of it like a recipe in cooking. Each step leads you closer to the final dish. Algorithms are everywhere, from sorting your emails to finding the fastest route on a map. They form the backbone of computer science and are essential for making computers work efficiently. In this video, we'll explore the key concepts, types, and real-world applications of algorithms, making the topic accessible and engaging for everyone. Understanding algorithms is crucial for anyone interested in technology or problem-solving. Algorithms help us break down complex problems into manageable steps, making solutions more efficient and reliable. Whether you're coding a new app, analyzing data, or simply organizing your daily tasks, algorithms play a vital role. By studying algorithms, you gain the tools to optimize processes, save time, and even innovate in fields like artificial intelligence and data science. Throughout this video, we'll see how algorithms impact our daily lives and why mastering them is a valuable skill. It's important to distinguish between an algorithm and a program. An algorithm is the logical plan, a sequence of steps to solve a problem. A program, on the other hand, is the implementation of that algorithm in a specific programming language. Think of the algorithm as the blueprint, and the program as the finished building. This distinction helps clarify how algorithms can be applied across different platforms and languages, making them a universal concept in computer science. Algorithms aren't just for computers, they're part of our everyday routines. For example, when you follow a recipe to bake a cake, you're using an algorithm. When you sort your books by size or color, that's another algorithm at work. Even deciding the order in which you complete your daily tasks can be seen as an algorithm. These real-life examples show that algorithms are all about organizing steps logically to achieve a goal, whether in the kitchen, at work, or in your personal life. Every algorithm shares some core properties. First, algorithms must be clear and unambiguous. Each step should be precisely defined. Second, they must be finite, meaning they eventually come to an end. Third, algorithms should be effective, using basic operations that can be performed in a reasonable amount of time. These properties ensure that algorithms are reliable and can be executed by both humans and machines. Understanding these characteristics is key to designing strong algorithms. Algorithms typically start with input, data that is provided to solve a problem. After processing this input through a series of steps, the algorithm produces an output, which is the solution or result. For example, in a sorting algorithm, the input is a list of numbers, and the output is the sorted list. Understanding how input and output work is fundamental to designing algorithms that are both useful and efficient. Algorithms can be deterministic or non-deterministic. A deterministic algorithm always produces the same output for a given input, following the same steps every time. Non-deterministic algorithms, on the other hand, may yield different results even with the same input, often using randomness or parallel processes. Understanding this distinction helps in choosing the right algorithm for a specific problem, especially in fields like cryptography or artificial intelligence. Efficiency is a key consideration in algorithm design. Efficient algorithms solve problems using the least amount of resources, such as time and memory. For example, searching for a name in a phone book can be done quickly with a binary search algorithm, compared to checking each name one by one. We'll explore how to measure and compare algorithm efficiency using concepts like time complexity and space complexity in upcoming scenes. Time complexity measures how the running time of an algorithm increases as the size of the input grows. It's usually expressed using big O notation, such as O(n) or O log n. For example, a linear search algorithm has a time complexity of O(n), meaning the time taken grows proportionally with the input size. Understanding time complexity helps you choose algorithms that scale well as your data grows. Space complexity refers to the amount of memory an algorithm uses relative to the input size. Like time complexity, it's often described with big O notation. Some algorithms use more memory to achieve faster results, while others are more memory efficient but may take longer to run. Balancing time and space complexity is a crucial part of algorithm design, especially when working with large datasets or limited resources. Big O notation is a mathematical way to describe the efficiency of an algorithm. It focuses on how the algorithm's performance changes as the input size increases, ignoring constant factors. For example, O(1) means constant time, O(n) means linear time, and O(n)(2) means quadratic time. Big O helps you compare algorithms and choose the best one for your needs. There are several common types of algorithms you'll encounter. These include sorting algorithms, searching algorithms, recursive algorithms, and greedy algorithms, among others. Each type is suited to different kinds of problems, and understanding their strengths and weaknesses helps you pick the right tool for the job. In the next scenes, we'll dive deeper into some of these algorithm types. Sorting algorithms arrange data in a particular order, such as ascending or descending. Common examples include bubble sort, merge sort, and quick sort. Sorting is essential in many applications, from organizing files to optimizing search results. Each sorting algorithm has its own advantages and trade-offs in terms of speed and memory usage. Bubble sort is one of the simplest sorting algorithms. It works by repeatedly stepping through the list, comparing adjacent elements and swapping them if they're in the wrong order. This process continues until the list is sorted. While easy to understand, bubble sort is not very efficient for large datasets as its time complexity is untouched. Merge sort is a more efficient sorting algorithm that uses a divide-and-conquer approach. It splits the list into smaller sublists, sorts each sublist, and then merges them back together in order. Merge sort has a time complexity of n log n, making it much faster than bubble sort for large datasets. It's widely used in computer science for its efficiency and reliability. Quicksort is another popular sorting algorithm. It selects a pivot element and partitions the list into two sublists, one with elements less than the pivot and one with elements greater. It then recursively sorts the sublists. Quicksort is efficient on average with a time complexity of log n, but its worst-case performance can be slower if the pivot choices are poor. Searching algorithms help you find specific data within a collection. The two most common types are linear search and binary search. Linear search checks each element one by one, while binary search divides the list in half each time, making it much faster for sorted data. Choosing the right search algorithm depends on the size and organization of your data. Linear search is the simplest searching algorithm. It starts at the beginning of the list and checks each element until it finds the target or reaches the end. While easy to implement, linear search can be slow for large datasets as it may need to check every element. Its time complexity is O(n), meaning performance decreases as the list grows. Binary search is much faster than linear search, but it only works on sorted lists. It starts by comparing the target value to the middle element. If the target is smaller, it searches the left half; if larger, the right half. This process repeats until the target is found or the list is exhausted. Binary search has a time complexity of O log n, making it highly efficient for large, sorted datasets. Recursive algorithms solve problems by breaking them down into smaller, similar subproblems. The algorithm calls itself with a simpler version of the original problem, continuing until it reaches a base case. Recursion is powerful for tasks like calculating factorials, traversing trees, or solving puzzles. However, it can use more memory due to repeated function calls. Greedy algorithms make the best choice at each step, hopping to find the global optimum. They work well for problems like finding the shortest path or making change with the fewest coins. However, greedy algorithms don't always produce the best solution for every problem, so it's important to know when to use them. Divide and conquer is a strategy where a problem is divided into smaller subproblems, each solved independently and then combined for the final solution. Merge sort and quicksort are classic examples. This approach is powerful for handling large, complex problems efficiently as it breaks them into manageable pieces. Dynamic programming is a technique for solving complex problems by breaking them down into simpler subproblems and storing the results of these subproblems to avoid redundant work. It's especially useful for optimization problems, like finding the shortest path in a graph or calculating Fibonacci numbers efficiently. Dynamic programming can greatly improve performance by reusing solutions. Backtracking algorithms try to build a solution step by step, abandoning choices that lead to dead ends. This approach is often used in puzzles such as Sudoku or the n-queens problem. Backtracking is powerful for exploring all possible solutions, but it can be slow if the search space is large. Brute force approach tries every possible solution to find the best one. While simple and guaranteed to work, brute force is often inefficient for large problems because it checks all possibilities. It's useful for small datasets or when no better algorithm is available, but usually not practical for complex tasks. There are several techniques for designing algorithms, including divide and conquer, dynamic programming, greedy methods, and backtracking. Each technique has its own strengths and is suited to different types of problems. Mastering these techniques allows you to tackle a wide range of challenges efficiently. Analyzing algorithms involves evaluating their efficiency, correctness, and resource usage. This process helps you understand how an algorithm will perform in different situations and whether it's the best choice for your problem. Key analysis tools include time complexity, space complexity, and empirical testing. An algorithm is correct if it produces the right output for all possible valid inputs. Proving correctness often involves mathematical reasoning or testing with a variety of cases. Ensuring correctness is essential before deploying an algorithm in real-world applications, as errors can lead to unexpected results or failures. Stability is an important property in sorting algorithms. A stable sorting algorithm preserves the relative order of equal elements. This can be crucial in applications where the original order carries meaning, such as sorting a list of people by age while preserving alphabetical order for those with the same age. Sorting algorithms can be in place or out of place. In-place algorithms rearrange the data within the original structure, using minimal extra memory. Out-of-place algorithms require additional memory to store the sorted data. Understanding this distinction helps you choose the right algorithm based on your memory constraints. Algorithmic paradigms are general approaches to problem solving, such as divide and conquer, dynamic programming, greedy methods, and backtracking. Each paradigm offers a unique way to tackle problems, and understanding them helps you select the most effective strategy for your needs. Algorithms are used in countless applications, from web search engines and social media feeds to navigation systems and financial modeling. They help automate tasks, analyze data, and make decisions. Understanding algorithms opens doors to innovation in almost every industry. Visualizing algorithms can make complex concepts easier to understand. Tools and animations can show how data moves and changes during each step of an algorithm. Visualization is especially helpful for learning, sorting, and searching algorithms as it brings abstract ideas to life. Pseudocode is a way to describe algorithms using plain language and simple structures without worrying about programming syntax. It helps you focus on the logic and steps of the algorithm before translating it into code. Pseudocode is a valuable tool for planning and communicating algorithm designs. Flowcharts are diagrams that represent the steps of an algorithm visually. Each step is shown as a box with arrows indicating the flow of control. Flowcharts make it easier to understand and debug algorithms, especially for complex processes with many decisions. Optimization involves improving an algorithm to make it faster, use less memory, or be more reliable. This can mean choosing a better algorithm, tweaking parameters, or rewriting code for efficiency. Optimization is a key skill for programmers and engineers, especially when working with large-scale systems. Not all problems can be solved efficiently with algorithms. Some problems are too complex, requiring enormous time or memory, while others are unsolvable by any algorithm. Understanding these limitations helps you set realistic expectations and look for alternative solutions when needed. NP-complete problems are a class of problems for which no efficient algorithm is known. These problems are easy to verify but hard to solve and include famous examples like the traveling salesman problem. Understanding NP-completeness is important for recognizing when a problem may not have a practical solution. Heuristic algorithms use practical methods to find good enough solutions when perfect answers are too costly or impossible. They rely on experience, rules of thumb, or approximations. Heuristics are common in fields like artificial intelligence, where exact solutions may be impractical. Randomized algorithms use random numbers to make decisions during their execution. This can help solve problems faster or avoid worst-case scenarios. Randomized algorithms are used in areas like cryptography, optimization, and simulations, offering unique advantages over deterministic approaches. Parallel algorithms divide a problem into parts that can be solved simultaneously on multiple processors. This approach can greatly speed up computation, especially for large datasets or complex calculations. Parallel algorithms are essential in modern computing, from scientific research to big data analysis. Testing algorithms is crucial to ensure they work correctly and efficiently. This involves running the algorithm with various inputs, checking outputs, and measuring performance. Testing helps catch errors, optimize performance, and build confidence in your solutions before deploying them in real-world applications. Documenting algorithms is important for sharing your work with others and maintaining your code over time. Good documentation explains the purpose, steps, and usage of the algorithm, making it easier for others to understand and improve upon your work. Learning algorithms takes practice and patience. Start with simple problems, study existing solutions, and gradually tackle more complex challenges. Use visualization tools, write pseudocode, and test your algorithms to deepen your understanding. With time, you'll develop strong problem-solving skills and confidence in algorithm design. Algorithms are the foundation of computer science and technology. They help us solve problems, automate tasks, and innovate in countless fields. By understanding and mastering algorithms, you gain the ability to tackle complex challenges and create efficient, reliable solutions. Keep exploring, practicing, and applying algorithms to unlock new possibilities in your studies and career.